Hi all, today we are going to look at dot convention. Dot convention. So this convention is related to mutual inductance. Dot convention for mutually coupled pair of coils. Dot convention for mutually coupled pair of coils. What it is? Okay, let's consider that we have a magnetic core, something like a transformer core, like this, and then there are a pair of coils, copper conductors, like this. It comes back and goes like this. Okay, so this is one end of this coil and this is another end of this same coil. Similarly, here again we have another coil which goes like this. Let me name them as coil A terminal 1, coil A terminal 2, here coil B terminal 1 and coil B terminal 2. Now if I pass a current, say I here, then this current flows like this and it will generate a magnetic flux lines through this coil. Now how can we determine the direction of these flux lines? Okay, so here is the rule. Say if we look at these coils from the bottom, say from here, then the current is flowing in a clockwise direction. Okay. So if we look from the bottom of this coil, so you see that the current is going from left to right and then going down, then from right to left and then coming up, and then again left to right, going down, then right to left, coming up. So this is rotating in a clockwise direction as seen from the bottom of this core. Now this clockwise direction is equivalent to a south pole. How to remember? Okay, to remember this, just draw two true arrows at the two ends of S. So this indicates a clockwise rotation. So therefore, this is how to remember that a clockwise direction of current is equivalent to a south pole being generated as seen from this direction. So this side is south pole. Similarly, if we look from the top, we will see the current is rotating in the opposite direction, that is anti-clockwise direction. So here we will have a north pole. Once again, if we draw two arrows like this, this indicates a anti-clockwise or counterclockwise rotation. So that's how we can remember it. So this is a south pole, this side is the south pole, this side is the north pole. That means the flux line comes out from the north pole, goes like this, and then it comes back and enters through the north pole. So enters through the south pole. So comes out through the north pole and goes back through the south pole. Okay, so this is how the flux lines are. Now if this current I is a constant current, then this flux is also constant, and if the flux is constant, then no EMF is induced in any of these coils. However, if this current is changing, then this flux line, the amount of flux also changes, and that changes the flux linkage of these coils, and that EMF is induced in these coils. For example, if IT, that is current is a function of time, if it is increasing, then this flux is increasing and some EMF should be generated in this coil. Now, how to determine the direction of this induced EMF? We can use Lenz's law for this. So, Lenz's law we are going to use. Now, Lenz's law says that the induced EMF will be in such a direction so that will try to drive a current through this coil in such a direction which opposes the increase of this flux. So, when IT is increasing, if IT is increasing, say IT is increasing, then this flux phi is also increasing. Therefore, the EMF induced in this coil should try to reduce this flux, or in other words, should try to generate a flux in the opposite direction. So the induced EMF should try to drive a current in the opposite direction to this current IT, and therefore this side will be plus and this side will be minus. So thus this will try to drive a current in an opposite direction to the current IT. When IT is increasing, flux phi increases, but this induced EMF tries to drive the current in the opposite direction so that the flux could be reduced. So this side is plus and this side is minus. That's what we have found using Lenz's law. Now we can apply Lenz's law again for this coil to determine what will be the polarities of the induced EMF in this coil. So in this coil, once again, the EMF should be in such a direction so that it tries to reduce this flux, or in other words, it tries to generate a flux in the opposite direction. So that means it should try to generate a flux in upwards direction, or it should try to make this side as north and this side of this coil as south pole. Now to make this side as south pole, the current should rotate in a clockwise direction. Therefore, the current should rotate like this. So the induced EMF will try to send a current in this direction, which when seen from the bottom of this limb looks like a clockwise rotation of current. Thus, this side will be plus and this side will be minus, so that current goes like this. So if this circuit was closed, then this induced EMF would drive a current in this direction from B1 to B2 and then here like this. Okay, so therefore this side becomes plus and this side becomes minus. Why? Once again, because only if this is plus and this is minus, this will try to drive a current in a direction which opposes the increase of this flux. In a similar way, if this current IT is decreasing, so if IT is decreasing, you will see that this will generate a minus and a plus polarity of induced EMF at respectively A1 and A2. And similarly, when this current is decreasing, it will generate a plus at B2 and minus at B1. Okay, so therefore we see that these two terminals A1 and B1, they always have similar polarities. When this current increases, A1 and B1, they have simultaneously plus polarity or positive polarity. When the current IT is decreasing, both A1 and B1 have a negative polarity. Similarly, A2 and B2 always have same polarity, same type of polarity, positive together or negative together. To indicate this, what we do, we put a common symbol alongside A1 and B1, something like a dot here and a dot here. So this same symbol along A1 and B1 indicates that the polarities of A1 and B1 are always similar, are always alike. Similarly, we can indicate A2 and B2 with a different symbol like a cross to indicate or to convey that A2 and B2 always have same polarity or similar polarity. However, if we just put two dots at A1 and B1, putting two crosses are redundant, not necessary, because once we say that these two terminals are similar, it's evident that these two terminals A2 and B2 are similar. So therefore, in general, we do not have to put this cross symbol. It's not necessary. Okay, this is useful when we cannot see what is or how is the winding made inside this transformer. Suppose we have this transformer like a black box, this transformer is in a sealed container, and we cannot see how the winding is made inside this container. We can only see 4 terminals, 2 input terminals and 2 output terminals, and then we may still want to know that how are the polarities of A1, A2 and B1, B2 related to each other. In such situations, putting a dot along A1 and B1 indicates that these two terminals are always similar, and these two terminals A2 and B2, they are always similar. Now let us check our understanding about the dot convention with some small exercises. So here are the exercises. So let's check ourselves. So exercise number 1. So here I have a core like this. and I have a pair of coils like this. One, and here is the other. Okay. The question here is, how can I put the dots along these two coils? Or say, if I put a dot here, where should I put the other dot? Should I put it here or should I put it here? Try this exercise yourselves, find the answer and take a break or pause the video before I tell you the answer. Okay, so now I'm going to tell you the answer. The answer is, we should put the dot here. Why? You can proceed using Lenge's law as we have done in the previous case, but in this case it's even simpler because we see that the two coils are on the same limb of this cord, and the sense of winding is also identical for both the coils. That is, if we see from the bottom, both the coils are rotating in a clockwise direction. Therefore, the dots should be, of course, intuitively or very clearly, the dots should be at the similar terminals here and here, or alternatively here and here. Now, let's do another exercise, a very similar one. Suppose this is my cord. And now I have a coil 1, then a coil 2, which is like this, and then a third coil, which is, say, like this. Sorry, this is not there. Okay, and a fourth coil, which could be like this. So once again, the question is, if I put a dot here, where will be the dots in all these other three coils? Here or here, here or here, here or here. Pause this video, solve this problem yourself, and I'll give you the answer. Check your understanding. Okay, so hope you have solved the problem. Now let me just give you the answer. So here the dot is on this side because these two coils are of course on the same limb, so the flux direction is always same through them. However, the sense of winding is opposite for these two coils, so when this becomes plus, this should be, or the dissimilar terminal should be plus, so we put two dots here. Similarly, for this coil, the dot you can find using Lenge's law that it should be on this side, on the upper side. Or actually, this is very much same as this previous diagram. If you do not, let me just put them side by side like this. So here you see that the primary side winding is similar to this green one, and the secondary side winding is similar to this one. If it looks dissimilar to you slightly, then let me put one more turn here and one more turn here. Now see that these two coils are exactly similar, so this side should be plus when this side is plus, or they should sit at the same dot. Now for this other coil, last coil, the dot should obviously be here because these two coils are on the same limb of the core. However, the sense of winding is opposite for these two. This is rotating in a clockwise direction as seen from the bottom. This one is rotating in an anti-clockwise direction as seen from the bottom. So the dot should be on the lower side. Okay, so that's how all the dots should be. If you have solved it correctly, that means you have understood the dot convention. Now let's come to a bit advanced discussion about dot convention. I mean, before I start, stating that this is a bit advanced concept to know, but it's useful to know, and once you know it, you'll say that it's not difficult at all. Okay, so the idea is that the dot convention is not transitive in general. What I mean by that, if I have three coils, say 1, 2 and 3, where the sense of winding is not known to us, say they are in some black boxes, or maybe that they are in a common black box, something like this, that there's a black box, we do not know what is exactly there inside, but we have 3 pair of coils. Let me draw them with different colors. And then they're connected, but we don't know exactly how these 3 coils are owned on the core, or how they are placed, on which side of the core they are placed. We do not have all these information. We have only 6 terminals, 2 for each of them at our disposal. Now if I put a dot here and here, indicating that these 2 terminals always have the same polarity. Similarly, if I put 2 dots, okay, let me do it like this. So these 2 dots, these 2 black dots, indicate that these 2 terminals are always of same polarity. If I put 2 green dots, or okay, let me use a slightly different symbol like this. So these 2 green dots indicate that these 2 terminals share similar polarity. It's not always true that these 2 terminals always share same polarity. In other words, let me name them A1, A2, B1 B2 C1 C2. If A1 and A2 have dots together, I meant A1 and B1 have dots together, A1 and C1 have dots together, that doesn't imply that B1 and C1 should have dots together always. I will show this with an example where this happens. So here is the example. Let's consider a code like this, a three-phase transformer. Okay. So we have a core, magnetic core like this. So this is the core. So this part is the magnetic material, is the iron core. Okay. And we have three coils wound on it like this. One, two, and three. So let me call them as A1, A2. This is C1, C2, and this is B1, B2. Okay. Now let's consider coil A and coil B together, forgetting coil C. Okay. So if we look at this diagram, we'll see that coil A and coil B we cannot use this diagram. Here coil B and this coil B are wound in opposite directions. Okay, we don't need it. We'll do it here. So see, the current IA, this is IA, is increasing. Okay, when IA is increasing, that means this current, as seen from the bottom, rotates in a clockwise direction. Therefore, this side should be south pole, this side should be north pole. So flux comes out like this, then comes like this, and here again it goes like this. Right, so here the coil B will try to generate an EMF such that to oppose this increase of flux. So it will coil B will try to generate a flux in upwards direction. Okay, so upwards direction means this side should be north, this side should be south. Okay, so if this should be south, that means the current, the coil B should try to drive a current in a clockwise direction as seen from the bottom. That means it will try to drive a current in this direction, right? Okay, so this side will be plus and this side will be minus. So I put a dot here along with this, right? So these two sides share the same polarity. Now here again, if I do the same analysis, I'll find that this side C2 should be positive when A1 is positive. So A1 and B2 have similar polarities. A1 and C2 have similar polarities when a current IA is increasing, right? So we see here that A1 and B2 are similar, A1 and C2 are similar. Does that mean B2 and C2 are similar? So I put a question mark. A1 and B2 are similar, A1 and C2 are similar. Does that mean B2 and C2 are similar? I have a question mark. Let's analyze. So in the previous analysis, we have driven a current through coil A, and these two coils remained passive. So coil A was active, these two coils were passive. Now let's drive a current, say through either of these two coils. Let me take, say, this coil B as my active coil. Now, so this is IB. Okay, so IB is in this direction, which is if when seen from the bottom is in a clockwise direction. When IB is in clockwise direction and increasing, then the flux, let me use a different color, the flux comes out like this and then goes like this here in the opposite direction, then it comes like this, but here in the opposite direction as before, unlike before, and it enters. Right? Now if this flux is increasing because IB is increasing, we can again use Lenz's law and find out the direction of EMF in coil C, and we'll see that C2 should be positive. C2 is positive when IB is increasing. Now when IB is increasing, B1 is positive. So then B1 is positive. So that means C2 and B1 should share a similar dot. So this implies B1 and C2 should have dots together. Or in other words, B2 and C2 should not have dots together. Okay, so here the question that I asked before, whether B2 and C2 should share same dots, the answer is no. Right? So the message from this discussion is that if we have a black box like this, and if we really don't know how the coils are wound up inside this black box, then putting dots for these three coils or more than two coils is difficult, right? If we put dots for at A1 and B1 together, again at A1 and C1 together, that doesn't mean that B1 and C1 have similar polarities always, or they should have similar dots. Okay, as I already told that this is a bit advanced discussion, but once you understand this, you will realize that it's not difficult. And if you do not understand, I think there is nothing much to worry about, because as I already told, this is a bit advanced discussion.